Proof of the observation 6.27. In general, there is no algorithm to deduce an automaton for a regular language from a machine description of the language. Proof. We define a family the set Vs of x such that x is an n of a recursive functions with Vx of x of y equals to 1 if Vx of x holds, and the Vx of x of y not holds otherwise. Hence, Vx denotes the xth partial recursive function. Let Vx equals to dom of Vs of x. Then Vx is either empty or n, and furthermore, Vx equals to n if Vx of x holds. Now, since we can easily see if a language is empty or not from an automaton for L, if we could construct the automata for the Vx, then we could decide if Vx equals to the empty set or not, and hence decide if Vx of x holds. This contradicts the algorithmic undecidability of the halting problem. Despite the observation 6.27, we can deduce an automaton if we additionally know, for instance, some bound on the number of states of such an automaton. The method of test sets allows to solve the following promise problem. Input a decision procedure for a language L. Promise L is regular and there is some M accepting L with at most k states. Question. Can we compute an automaton M prime accepting L? Theorem 6.28. The promise problem above is solvable and furthermore, we can compute M prime with at most k states accepting L. Proof. The idea is simple. We use the proof 321 of theorem 6.21. The machine is described by items 1 to 4 of that proof. The only fact that we need to check is that we can decide if x congruous L to y for x and y in L. By definition, x congruous L to y if and only if for all z in L, x z in L if and only if y z in L. Suppose that M is an automaton accepting L with n states, and x is not congruous L to y. We claim that their sum z in sigma star with the length of z which is less than equals to n, and z a witness to x not congruence L to y. The point is that there is some z prime such that say x z prime in L, yet y z prime not in L. This means that if we input x z prime into L, we will get to an accept state, and if we input y z prime into M, we must get to a non-accept state. But since there are at most n states in M, the longest path from one state to another can have length n. Thus, we can refine z prime down to a string of length less than equals to n by deleting all loops. Thus, there is some z with the length of z which is less than equals to n, witnessing that x is not congruent L to y. Hence, to decide if the set x equals to the set y, we simply need to go through all z in sigma star with the length of z which is less than equals to n, and see if for these z, x z in L if and only if y z is in L. The same reasoning demonstrates that for all x in sigma star, there is some x prime in the set x with the length of x prime and the length of y prime which are less than equals to n. Hence, to implement the method of 321, we need only look at a table of strings of length less than equals to n and test them with strings of length less than equals to n. The fact that congruence L defines the coarsest congruence means that the number of states of M prime we obtain from this technique must be minimal. The reader should note that essentially the same proof shows that the following modified problem is solvable. Input: a decision procedure for a language L and a decision algorithm for congruence L. Question: can we compute an automaton M prime accepting L? Example 6.29. Here is an example of the method of test sets. We will pretend that we have been implicitly given a regular language over the star of 0, 1, and note that there is some automaton M with less than equal to 4 states accepting L. Suppose that we obtained the table of answers of table 6.1 from the decision procedure for L. We note that the set lambda equals to the set 1 equals to the set 1 1 equals to the set 1 1 1 equals to the set 1 0 0 equals to the set 0 0 equals to the set 0 0 1. And the set 0 equals to the set 1 0 equals to the set 1 1 0 equals to the set 0 0 0 equals to the set 0 1 0. And the set 0 1 equals to the set 1 0 1 equals to the set 0 1 1. Hence, the three states of M prime are the set lambda, the set 0, and the set 0 1. Note that the set 0 1 will be the accept state since 0 1 is in L. The transition diagram is given in figure 6.8. An important consequence of the proof of the Myhill-Nerode theorem is the fact that the automaton from the proof of the property 3 to 1 has the least number of states of any deterministic automaton accepting L. Implicitly, the proof provides us with a state minimization procedure. That is, we can take an automaton M accepting L and identify states equivalent under the congruence L. Again, since the number of states of L determines the length of the longest path in L, we only need to look at strings of length less than equals to the length of K. One minimization algorithm derived from these observations is given below. Algorithm 6.30 State Minimization Algorithm. Step 1. Make a table of entries PQ in K by K for P not equals to Q. Step 2. Route 1. For each PQ with P in F intersect Q not in F, mark PQ. Step 3. Repeat the following in routes until there is no change from one route to the next. Route I plus 1 for 1 less than equals to I. For all PQ pair not yet marked by the end of route I, if for some A in sigma, delta of PA, delta of QA is marked, then mark PQ. Step 4. Any unmarked squares representing PQ represent states that are equivalent and hence can be identified. In figure 6.9, we give an application of the minimization algorithm. We remark that in route 2, the only unmarked xy are AE, BC, BD, and DC. We mark CD since delta of C0 equals to D, delta of D0 equals to E, and DE was marked in route 1. We mark BD since delta of B0 equals to D, and delta of D0 equals to E, and finally, we mark EA since delta of E1 equals to E, and delta of A1 equals to B. In route 3, there is no change from route 2 and the algorithm terminates. Notice that the cost of the algorithm is at most the big O of n squared if M has n states for a fixed sigma.